Hi, we've now reached the final video of the exponential and logarithmic functions video series. This is video 7 and we're looking at integration and the logarithmic function. So let's get stuck into it. Okay, we've got a basic result and we've got a related result, a bit like bit similar to how we had a basic result and a useful result in our derivative of the log function. Now basically what we're saying here is that if you're integrating an expression here whereby the top is the derivative of the bottom, we can just write out our answer as log e of the bottom plus c. Now we'll get the hang of this. It's a bit gobbledygook at first. It sounds a bit Swahili, but still. The related result is, on this right hand side, if the top, you'll notice that's f dash x, is the derivative of the bottom, then we should get log e of just the bottom plus c. I missed out on a dx in there, but that's a technicality. So in plain English then, to recap, the pattern is if we integrate a fraction in which the top of the fraction is the derivative and the bottom is just the function, then the resulting answer is log a, or actually log e there, log e of the bottom plus c. Log e of the bottom plus c. Okay, let's have a look at some specific examples. Now, just bear in mind, I want to warn you here that we often have to adjust the original question, particularly in the harder ones, in order to arrange for that scenario to be true, that the top is the derivative of the bottom. So these adjustments, we'll show you how we make those, but just be aware that we don't always have that perfect arrangement to begin with, and we have to adjust and compensate to achieve that process. You'll see what I mean as we get into it. Now here, this is an indefinite integral. We don't have any x values to plug in later or anything, but this is a beautiful sight for a mathematician or even a math student for that matter, because the top is already the differentiation of the bottom. So our answer for that integration is log to the base e of just the bottom plus our c. Because the top is the derivative of the bottom already, we can just write that out straight. Don't really have to think about it all that much. That's the pattern we're trying to achieve anyway. Okay, now this one here down the bottom, this is one of the ones that we might have to adjust, because let's just analyze this one. Oops, let's not just yet. Okay, let's chat through this one. So this one I would call, this top one that we just had a look at, sorry about jumping around a bit, this one is the ideal, where it's already the scenario where the top is the differentiation of the bottom. Okay, now here our top needs to be what? Have a look at it. Our top needs to be the differentiation of the bottom. Now the differentiation of the bottom is 3x squared. Now on the top here we only have an x squared, so we would love to have a 3 on the top as well. So we adjust by multiplying by 3 on top. So if we adjust there, we're going to make it equal to integral 3x squared over x cubed plus 7 dx. Now that's great. We can't, unfortunately, mathematically speaking, just decide to multiply the top of something by 3 and hope to get away with it. We also must, what I'd call, well, here's the word adjust. I'm going to use the word compensate. We've multiplied the top by 3, and here we're going to compensate by multiplying by 1/3, because 1/3 times 3 ends up being 1, and compensating. So if we multiply something and then find 1/3 of it, we're back to the beginning really. But so all we're achieving is changing the format of this into a more ideal process. Okay, we must, and we'll do that out the front. So we've adjusted our original question so that the top is the differentiation of the bottom. Now our compensation of a third must go out the front there. And once we have that, that compensation stays for our final answer. We have a third, and because our section here now is ideal, we can say that the integral of that is log to the base e of just the bottom plus c. Now let me recap. This was not an ideal situation in example 2, unlike example 1, but it was close. If we had 3x squared on the top from the beginning, that would be fantastic, but we didn't. So we can go in and make it work like that. So we can have a 3x squared on the bottom, and to achieve that we'd need to multiply the top by 3. To compensate, we have to put a 1/3 out the front. So any compensation is really an inverse compensation to what we did to the function to make it ideal. Once it fits into that pattern of the top being the differentiation of the bottom, we can write it out with the compensation here, compensation out the front. This bit here is really just log e of the bottom plus c. So we're desperately trying to get it into the arrangement where we can just go ahead and follow the rule, really. Okay, here's a pretty tricky example, but we're going to go step by step. We're going to try and make the top the differentiation of the bottom. And we've also got an extra bit here where we're substituting in values of 4 and 3. That's why you notice that the heading here is now definite integrals. We don't need to put any plus c's in there. We're going to sub in x values and get our results that way. Okay, so let's analyze this a little bit. Ideally, the top of this equation, this integral, in order for the top to be the differentiation of the bottom, if we differentiate the bottom of x squared minus 2x, we would want the top to be 2x minus 2, but it's not. So how do we make that top of x minus 1 into 2x minus 2? We're going to adjust by multiplying by 2 on the top, because if you notice, when we expand 2x, 2 outside of x minus 1, we'll get that ideal top happening. And when we do that, we obviously have to compensate for that. Now, what's the compensation of multiplying by 2? Multiplying the front by the inverse of that, which is a half. You can always check whether you're adjusting and compensating correctly, because the product of your adjustment and your compensation should always work out to be equal to 1. Okay, let's have a look as we piece together this now that we've done a bit of compensating. So we've turned our question in. We've adjusted our question to be more ideal, really. It's a bit cheeky of us, but still. Our top is now the differentiation of our bottom. And we've got that compensation of a half out the front here. And we can go to it now, because it fits the ideal, or at least sections of it do. And we can then stub in the 4 and the 3. Once this section here is ideal, we can write it out like that. We have to keep our compensation here and here as well. But now we've actually done the integration now, and this is our setup in square brackets. And we're going to, as you know, sub in the 4 through wherever there's an x, then put a big minus and sub the 3 in wherever there's an x. Let's see how that works out. So here you can see that I've substituted 4 in wherever there's an x and 4 in wherever there's an x. Then we've got a big minus sign in between and a big bracket, and we've subbed in 3 in the 2x spots. So that's showing you how we write that out. Very similar to our previous definite integral process. To continue on here, I'm just simplifying these down. 4 squared is 16, 2 4s are 8, 3 squared is 9, 2 3s are 6, so that's nothing more than a simplification line there. And moving on, we're just simplifying the brackets here as well, and away we go. There is one version, you'll notice there's a half and a log e in both of those, but anyway, we can type that into our calculator at that point. There's a few log laws and things we could even process there, but not all that necessary. Remember, log e on your calculator, log to the base e, is a button that looks like an L and an N. So that's where we'd need to, that's the button we'd need to use in putting that into our calculator carefully. And this question, as we look back to the format they want, said 1 decimal place, and so we rounded off to 0.5. Quite a process, but in one way it's not much different to example 2, in that we are trying to desperately to adjust the top, so it's the top here, so it's the differentiation of the bottom. If we have to adjust by multiplying by something, we have to compensate out the front here so that everything's fair. It's a bit like saying whatever you've done to the top of a fraction, you've got to do to the bottom, or whatever you've done to the left-hand side of an equation, you do to the right-hand side. So I hope that helps. They're pretty complex ones, but once you get the scenario where the top's the differentiation of the bottom, that's what we're aiming for, because then we can write out that log E result to our integration and go from there. Hope that helps. If that was a bit fast, ask your local maths teacher. I'm sure they can help you. Thanks a lot. That's the end of the total series of exponential and logarithmic functions. I hope that's been of help to you. Watch them as many times as you like. Thanks. Bye.